So today I want to talk about number systems. And in particular, I want to give a brief overview of what are probably the four most common number systems that show up in mathematics. And that is the natural numbers, which are a subset of the integers, which are a subset of the rationals, which are a subset of the reals. So we're going to start with the natural numbers and work our way up. The natural numbers are like the counting numbers. So this set includes 0, which maybe is slightly counterintuitive, but that's just how we define it. It starts with 0. Then it goes up 1, 2, 3, 4, and so on. They're called the natural numbers because in some sense these are almost like what's given to us. We can count things. We can distinguish some number of things. There are 3 pieces of chalk right here. There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 distinct symbols that I just wrote down in this line. Stuff like that. The natural numbers also have operations on them. For example, I can do 2 plus 3 equals 5. So if I start with 2 natural numbers, I can get another one by adding them together. Or I can do 7 plus 0 equals 7. Another thing I can do with natural numbers is I can subtract them. So I can do 8 minus 6 equals 2. And again, I start with 2 natural numbers and I get another one, which is the difference between them. But of course, as you probably well know, if I start with some pairs of natural numbers, like 5 and 7, when I subtract them, I don't get anything which is representable with a natural number. 5 minus 7 is something below 0 in some sense. And so that leads us to Z, the integers. And the integers are a fairly conservative expansion of the natural numbers, where we say, look, I don't just want to have 0 and 1 and 2 and 3 and so on all the way up. I also want to have -1 and -2 and so on all the way down. So I've sort of symmetrized my number line here so that when I do something like 5 minus 7, I get -2. In other words, I start with 2 integers, I subtract one from the other, and I get an integer. So the movement from the natural numbers to the integers can be viewed as a kind of demanding a kind of closure property. Closure meaning that, look, if I start with 2 integers and I subtract one from the other, I want the answer to be an integer. And that's just not true for natural numbers. If I start with 2 natural numbers and I subtract one from the other, sometimes the answer is a natural number, sometimes it's not. Now the same reasoning about closure can bring us one step upward to the rational numbers. And the rational numbers intuitively are all the fractions. And maybe a bit more formally, I can write this as all the m divided by n, such that m and n are themselves integers. So, for example, half is a fraction, so is 3 over 5, so is -2 over 17. I can write some fractions in more than one way. So, for example, 2 over 4 counts as a fraction, but I think of it as being equal to 1 over 2. -3 over -6 is another way of writing 1 over 2 because of the 2 negatives here cancel each other out and we just get 3 over 6, which is like 1 over 2, and so on. Now the way that I write down fractions suddenly has this new property that we didn't have before for the natural numbers and the integers, which is that, like I was just saying, there's more than one way of writing down the same fraction, right? I want to treat these 2 guys as being equal. And a sort of analog to that in the integers is, for example, we saw that 5 minus 7 equals -2, but another way of getting -2 would be, for example, 10 minus 12. So you can think of these 2 expressions here as 2 ways of writing down -2, and that's sort of analogous to how 1 over 2, which you think of as half, 0.5, can also be written as 2 over 4. And in terms of closure properties, well, the natural operation that we're closing under to get the rational numbers is division, right? It's possible to start with two integers and divide one by the other and get an integer. For example, we can start with 6 and divide it by 2, and we know that that's going to give us 3. Or we can start with 18 and divide it by -6, and the way that the division of negative numbers works, this is going to give us -3, and so on. But if I start with 18 and divide it by 7, this is not an integer. So just like we got the integers from the natural numbers by saying, I want to be able to subtract things and still have something that counts as a number, and that's what integers do. The rational numbers can be viewed as saying, I want to be able to divide my numbers one by the other and get something that still counts as a number. So for example, if I take a fraction like 2 over 3, and I divide it by another fraction like 7 over 8, a sort of familiar manipulation from high school tells us that this is equal to 2 over 3 times 8 over 7, which is 16 over 21. And we see that even if I start with two fractions, I'm getting a fraction out of it. So in other words, the rational numbers, this isn't a proof, just an example, but the fact is that the rational numbers are closed under division, right? With the one exception being that we do not write division by 0. So I don't write 2 divided by 0. This is a no-no, which means over here, when I was trying to write down the set of all fractions, I should have been a little bit more careful and said, yeah, these are all fine, except I shouldn't ever choose n to be 0 in this case. All right, so that gives us the natural numbers, the integers, and the rationals. What's left? Well, what remains are the real numbers. Which, even by the name, you can kind of see are taken by many, and many mathematicians in particular, to be the sort of the underlying substrate of numbers. These are the numbers that really exist in some sense. This is debatable, but whereas the natural numbers came to us very easily just by counting things, and the integers and the rationals come to us by wanting our number system to be closed under certain operations, the reals can also be viewed as coming to us in that way, but are perhaps more easily seen to be forced on us by something like, for example, the proof that the square root of 2 is not a rational number. So this is something that I proved in another video. The square root of 2 by Pythagorean's theorem is if I have a triangle with side lengths 1 and 1, then I know that this hypotenuse, the length of the hypotenuse, satisfies the equation x squared equals 1 squared plus 1 squared equals 2. So x has to be the square root of 2. And I've shown that the square root of 2 is not rational. So if we want our number system to be closed under square roots, then I need to add something more to the rational numbers. So I guess it is a kind of closure property. But actually, asking that the rationals be closed under square roots doesn't get us all the way up to the real numbers. It gets us some extra things. But to really see what gets us to the real numbers, what we really want is closure under limits. And in this video, I can't be completely precise about this, but the intuition works like this. Here I can write down a number like 2.1. And this is a fraction. This is equal to, for example, 21 divided by 10. I can also write down a number like 2.12. And this could also be written as a fraction. This is equal to 212 divided by 100. And no matter how long of a decimal I write down, I can always write it as a fraction by dividing by an appropriate power of 10. But what if I carry that process of describing a number with its decimal expansion to the limit, so to speak? What if I write down a number like 2.123879222 at any finite stage of this process, I get something which is a rational number because it can be written as a fraction. But what about the whole number? Right? I'm engaging your intuitions here. What about the whole number all the way? Well, actually, we know that some numbers, like for example 0.3333 threes all the way, it's fairly familiar, and I'll prove this in another video, that this is equal to 1 divided by 3. And in fact, you can show that any number like 8.676667676 and so on, where I keep repeating a part of it again and again, is also going to be equal to a fraction. I'll show this too in another video at some point. But what if I don't? What if I continue this decimal but without a repeating part? For example, I might write 0.101100100001, and so on, each time putting an extra 0 in between. There's a pattern here, but it's not a repeating pattern where there's some chunk that keeps getting repeated over and over again. Or what if I just have a seemingly unpatterned string of digits? If I want to count all of those as numbers, then I get the real numbers. And the real numbers can intuitively be laid out on a line. Here's 0, 1, 2, 3, -1, -2, -3. So I've got the natural numbers. I expand to the integers. I've got my rational numbers here, right? 3 over 2, 5 over 2. You can add in 1 over 4, and so on. And then I expand still further, and I added a number like 0.101001000, which is, I guess, somewhere over here. And the idea is that it fits into the number line, into an empty slot in between the fractions. And all of these decimal expansions fit into this line. And that's what the real numbers are. Now, none of this has been a formal definition, but I have, I hope, given you an idea of these four sort of most common number systems. I haven't told you about some intermediate systems like the algebraic numbers, or the complex numbers, or the hyperreal numbers, all of which fit into this picture, but the four sort of most standard ones are these four, and they sit nicely inside of each other like this.